Okay, this is week 3, implementing data technologies. So let's go to the first slide and take a little bit of an overview of what we're going to talk about. We're really going to talk about structured and unstructured databases, or relational and non-relational. There's a number of different terms. There's 3 terms we'll actually talk about, and I'll just brief you on them now. It's can either refer to as structured or unstructured, relational and non-relational, or SQL or no SQL databases. And we'll talk about what that means in a little bit. So depending on the task, data must be organized in certain ways. Can be used in a structured database, doesn't have to be. Without organizing that data, we're unable to translate it into useful information. So we do have to do some organization, have to have some sort of understanding of what's in the database, what sort of model is there. It can be very simple or very complex. There are 2 major ways to organize data, which we refer to as logical structuring, as opposed to physical structuring, which we'll talk about in a later lecture. There's also, we talked about relational and non-relational databases, and that's how we'll kind of divide up this lecture. And so in this segment of the class, what we specifically talk about is how to structure data, whether it's in a SQL or no SQL database, and how to represent structure in a model. We also discuss when it should be put into a relational model and when it may be better to keep it unstructured. So, and then the last thing we do is also talk a little bit about the technologies for structured and unstructured databases. Some of the ones that you may see when you enter into the job market or go out into the working world. So let's go to the next slide. Talk a little bit about data as a hierarchy, just to familiarize you with some terms as it relates to databases and database modeling. So for the purpose of this exercise, it's best to think of data as a hierarchy and the different elements of data as a hierarchy. So let's classify some of these elements. At the very top level, we have databases, the entire organized collection of data. A level below, we have files, a collection of related records. And so that may be a little bit of a confusing term. It's not necessarily like a Word document, when you think of a file. We're talking about files here. We're talking about something like the collection of records that make up a personnel file. And so one level below that is records, which is simply a collection of data fields. Basically, entities such as in a table about students, you may have the first name, the last name, the social security number, things like that. The collection of those fields makes up a record. And so one level below that, we of course have fields, and that is a name, number, or a combination of characters that describes an aspect of a business object or activity, such as first name, last name, etc. And the lowest level we have is characters, which are the letters, numbers, or special symbols that go into a field, that make up a field. And so there's the values of those fields, which are the characters, and then there's the classification of what those characters should be. And we'll talk a little bit about what that means here in a bit. So here's a pictorial of what I was talking about with regard to the hierarchy. You have databases such as a project database, personnel, and then within it you have personnel files, files about people, files about a department, or files that have to do with payroll, which is a good example because a payroll file is kind of a combination of something that comprises personnel and departments, so it can be a collection of those things. Files, of course, one level down, you have your personnel files, and they give you some examples there. You have records, which is a collection of fields that are usually in a table. Then you have fields, which, first name, last name, they give you the example of last name there, and characters, such as the letter F that might go into the field FISC. And of course, they give you the bitwise representation there. So moving on to the next slide, to talk a little bit more about the logical structure of data and what that actually means. So there's logical structuring of data, which we're going to talk about principally here, and then when we talk about computing and virtualization and hardware and things like that, we're going to talk about physical structuring of data at that point, where we talk about database virtualization and things like that. But right now we're going to focus on the logical structure of data. And so there's the data model, which is a diagram of data entities and their relationships. And then there's the types of different data models that you have that you see in software engineering or database administration or just out in industry. There's a generic database model that may show different databases and how they're connected to one another. Data structure diagrams, which offer a different type of pictorial of your data. Entity relationship models, which I conspicuously have in bold. Geographic data models, and which explain how your databases are located in terms of geography or topology or topography. And semantic data models, which talk about the topic of data semantics and how that exists in the World Wide Web. So for most database modeling, and what we're going to talk about here is the ERD, the Entity Relationship Diagram or Entity Relationship Model. I use these terms rather congruently because they pretty much mean the same thing. The diagram is the realization of the model or the conceptual model that we draw. So for database modeling, the ERD is the one used in the majority of data modeling scenarios. An ERD is basically a logical data model that uses a set of basic graphical symbols to show the organization of entities and relationships between data. Now, I understand you don't know what entities and relationships are. I'm going to explain those in the next slide, and we'll give some examples of how to develop these entity relationship models. Small fact, since I went to LSU, I actually studied under Peter Chen, who was an adjunct he splits his time between computer science and information systems at LSU, and he is the developer, the researcher who created the entity relationship model that's used throughout industry today. It's one of the most widely cited papers in computer science, and he is undoubtedly in the Computer Science Hall of Fame, with the Association for Computing Machinery. He's getting older and about to retire, but I was lucky enough to have a few years with him. Great human being, and I still see him at conferences every once in a while. So moving on to the entity relationship model and defining some of the terms that comprise it, there's a couple here. There's the notion of entities, there's attributes, data items, keys, primary keys, and relationships. And these are conceptual things, and what I'll do here as I'm talking is discuss how they're normally represented. So the first one we're going to talk about is entities, which is simply a generalized class of people, places, or things where data is collected, stored, and maintained. So what an entity basically ends up representing itself as is a table. Usually it's the class of people, places, or things where data is collected, stored, and maintained. That's usually a table, but the conceptual understanding of that is what we refer to as an entity. The conceptual definition of that is what we refer to as an entity. Then there is attributes, which are characteristics of an entity, and those generally manifest themselves as fields. So an employee number, last name, first name, hire date, department number, those are generally attributes. Then the next definition we have is data items, a specific value of an attribute. So that's simply the data that goes in the fields. That's all it is. And then we have the next one is key, a set of fields in a record that identifies the records. So this is where we distinguish between kind of regular fields and keys or fields that identify the records uniquely, so that you can key off of them. I mean, so you can actually use key as a verb. You can key off of those fields when you're searching it. So, for example, in the picture we have right next to the text here, we have employee number as a key field. And that's not only a key, that is the primary key, which is a field or set of fields that uniquely identifies the record. And so those two definitions could be a little confusing, so let me explain. You can have more than one field that uniquely identifies each record. They refer to that as a composite key. So let's say there's multiple people, over the course of history at a university like San Francisco State who have the employee number that we see up in the first record here of 005-10-6321. But they definitely are probably not both named, Francine Johns. So you could use the combination of employee number, first name, and last name maybe to uniquely identify who that employee is. And that collectively, that composite, makes up the primary key. So that's why it says in key and primary key, a field or set of fields that uniquely identifies the record. So the last one, so hopefully that explains it for you, because it can get a little confusing. I remember when I took this class, it was definitely a little bit confusing for me as an undergrad, so I certainly feel your pain there. So let's move on to the last definition that we have here, the last key term, and that's relationships. And so we have entities or tables, and we have relationships between those tables. And so that is collectively what makes up the entity relationship model. And we'll discuss and show examples of exactly what that means and how you characterize those relationships. Okay, let's move on to the next slide and talk a little bit about why we would use entity relationship modeling. So if you want to actually use a database, you have to understand actually how it's represented. You can have the data stored in some location, but you have to, have in your head or on paper or represented virtually a conceptual model of what you're going to search on. Even with non-relational unstructured databases, you still have to have some representation. You have to know what's in there, what you're able to search upon, search against. So an entity relationship model, in the case of relational databases, gives us a very formal representation of that data so that we can implement the model, we can search upon it. And we can also query, and so it says in the last bullet, we can query that data using our knowledge of this model. Let's look at some examples. So the first example of an ER model is what we have here. So you might not be able to do that yet, but couldn't you point out the following? In this model, we have entities, attributes, relationships, and we have different types of relationships that are represented by those little curved lines around the links between the entities and the diamonds that are in between the entities. So we'll talk about what these actually are, and we'll highlight what they are in the next few slides. Let's move on to entities and what they are. They represent objects or things of interest in a very conceptual sense. Physical things like students, lecturers, employees, products, different types of departments, things like that. Customers, of course. More abstract things as well, like order numbers or course numbers and data related to that. Entities generally have the following types of characteristics in a very general sense. They have a type or class. You classify your entities as lecturer, right, where you have a table of lecturers. And then they also have instances or values of that particular type, where one record or an instance would be me, lecturer Levy, right? So, and then also the third thing that is a type of characteristic that entities have are attributes that classify the values. So for example, name, email, first name, last name, email, phone number, office hours, things like that. Let's move on to how we would actually diagram entities. So an entity is usually drawn as a box with rounded corners. That's what's shown here in blue. It's generally drawn in a boxy shape. I've seen it in a number of different ways. UML might not represent it as a box with rounded corners, but that's, overall that's what you see. In the case of diagram of the entities here, those are the things that manifest themselves as tables for lecturer, module, and student. Right? Those are the entities, and then between them you have relationships, and then you have attributes. Let's move on to talk about attributes and exactly what those things are. So attributes are facts, aspects, properties, or details about an entity. So like we've talked about before, this notion of attributes represents itself usually as fields. Right? So for example, students, a record of a student, they have IDs, names, courses, addresses, address 1, address 2, city, state, zip, those are all separate fields. Another example is something like a module, like what's referred to here, might have a code, a title, how many credit weights, how many credits your class is, and different levels. And so attributes generally have the following types of characteristics. There's a name, usually your field has a name. An entity that's associated with it, right? It's usually part of a table. A domain or range of possible values. I'll give you an example. Your credit weights can't go above maybe 6, right? I mean, I don't think there's any classes at San Francisco that are worth more at San Francisco State that are worth more than 6 credits. So you would have a range of 1 to 6. Another domain or range of possible values, for example, is how you format that data. If you have a field called phone number, you want to make sure that it's 10 digits long, if it's a domestic phone number, of course. You might want to also make sure that it validates that it has a valid area code and a valid prefix, 3-digit prefix. So those are things that kind of fall within a domain or range of possible values that can be, validated or programmed into a database. An email address, for example, needs to have an @ symbol. If it doesn't, it falls out of the domain of range of possible values. So the last one, of course, we talk about is the values for those domains, which is essentially what I'm talking about now. There's the logical representation of the domain or range and how you classify it, how you might program that in, and then the actual values that go into the instance they belong to. Let's take a second and look at how we diagram attributes. So in an ERD, attributes are typically drawn as ovals. Each attribute's linked to its entity using a line, so you can see what that field is comprised of, or what that, entity is comprised of. And the name of the attributes is usually written in the oval. These, of course, are shown here in blue. Now, if we had a much larger entity relationship diagram than we have right here, it would certainly not have all of the attributes listed because it would simply make it rather visually unappealing and just a very crowded diagram. So usually a listing of those attributes would take place on a separate diagram or separate definition of as part of a comprehensive definition of the entity relationship diagram. So we've talked about entities and attributes. Now let's take a look at what connects them. So that's where we talk about relationships, which are an association between 2 or more entities. Each student, for example, takes several classes, right? That's an example of a relationship. Each class is taught by a lecturer. Each employee works for a single department. So you could reorganize this, reword those statements where you could say, 1 student takes many classes. 1 class is taught by 1 lecturer. 1 employee works for a single department. We'll talk about why that rewording is important here on the next slide. But relationships generally have the following characteristics. They usually have a name, a description, a set of entities that are part of that relationship, of course, a degree, the number of entities that participate. Most of all, everything we're going to do in this class is going to have 2. And then they have a cardinality ratio, and that's exactly why I reworded those 3 sentences that are listed at the top of the slide. So let's take a second and talk about what I mean when I say cardinality ratios. So the notion of cardinality is a mathematical term. It simply means the number of elements in a set when you're just talking about mathematics. And so we'll talk about how we apply those here in database modeling. Each entity in a relationship can participate in 0, 1, or more than one instance of that relationship. And so what this leads to is 3 types of relationships that parallel exactly why I was rewording those sentences on the last slide. So there's 3 types of relationship. There's a one-to-one relationship, such as each class has a single lecturer, one class has a single lecturer, or for the example here, one lecturer is assigned to one office. There's a one-to-many relationship where, for example, a lecturer may tutor many students, but each student has just one tutor. You could also say, a lecturer, a class, one class has many students, but, the converse, where each student has just, each student has many classes. And then you have a many-to-many relationship, where each student takes several classes and each class is taken by several students. The first 2 are quite common. The third one, many-to-many relationships, you're going to have to be careful about. So you're going to experience how to create these relationships when you do some modeling in your project during this class. And most of the time, dare I say all of the time, it's going to be one-to-one or one-to-many relationships. So let's take a look at how we diagram these relationships. I'll give you an example. So the relationships are the links between 2 entities. They're shown here in blue. They comprise the lines, an expression of what type of relationship it is, kind of by those little curvy lines, and the diamond, which gives the name of the relationship. So it articulates what this relationship is supposed to signify. Now, when you guys do your access, guys and girls, do your access projects, you're able to, drag relationships between tables. However, it doesn't depict them in this manner. And I think the way that they do this, where they have diamonds here, is particularly valuable so that you can name what the relationship is and means. And I think that's very important. And that's what separates what you do in Access from the modeling that you're going to have to do for your project. So, in this particular example, a lecturer can tutor many students. A lecturer tutors many students, so it reads very nicely. And a student studies many modules. So you have an example here of a one-to-many relationship with respect to lecturers and students. And then you also have a many-to-many relationship, as uncommon as I'll express that it may be, between students and modules. And you can see how they're related here, and I've given a small example in the visual below the text that shows what a one-to-many relationship means and how it's signified. So, let's talk a second about many-to-many relationships. They're usually very difficult to represent. While I gave an example on the last slide, most of the time, a many-to-many relationship can be split into 2 one-to-many relationships, or a number greater than one-to-many relationships. An entity represents, the many-to-many. The entities that we have on the previous slide showed a many-to-many relationship, but it's quite rare. And so when you're doing your projects, when you're enacting this, just know that if you think you come across a many-to-many relationship, take the time to try and decouple things and recharacterize exactly what you have, because that's usually what you can do, is you can split it up. Let's move to the next slide and talk about making entity relationship models. So to make an entity relationship model, you need to identify and ask the following questions, right? What are the possible entities? Also, what are the attributes of those entities? What might be the relationships between them? And what are the cardinality ratios of these relationships? To do this requires an accurate description of the business problem. And that's why, in the cases that we talk about, we spend a lot of time talking about the business problem, because that's really hard to conceptualize. And then it's even harder to take that conceptualization and put it into something that we can operationalize so that you can start to derive answers to some of those questions and think about your business problem in terms of the data that's there. So some general guidelines related to making ER models. Entities are things. They're objects or nouns found in the description of the business problem. Attributes are facts, right? They're many times nouns, but properties about the entities. Relationships are many times verbs. They're actionable. They often describe the relationships between these two entity nouns. So, we've talked a lot about about the concepts behind entity relationship models and how you might go about doing it. Now, let's give a small example. So, a university consists of a number of departments. Each department offers several courses. A number of modules make up each course. Students enroll in a particular course and take modules toward the completion of that course. Each module is taught by a lecturer from the appropriate department, and each lecturer then tutors a group of students. So, this is written in a very succinct form, and one of the difficulties when you're conceptualizing business problems, when you're out in the real world, is getting things to this succinct form. This takes a lot of work. But for the purposes of this exercise, of course, we're going straight to this very succinct text so that we can talk about how we would diagram this on the next slide. So here's a diagram that pretty much captures all of the things asked for, if you will, in the last slide, where you can see that there's a many-to-many relationships with modules and students, one-to-many relationships between lecturers and modules, a one-to-many relationship between departments and lecturers, and a number of different relationships here. Interesting is that you also have a many-to-many relationship between courses and modules. As it makes sense that there can be many modules assigned to courses, and courses can include many modules. So what you have here is a reasonably complex data model. It doesn't need to get too much more complex than this for the purposes of your project. So this actually serves as a very good example of what you can do for your project, or how you can model for your project. Of course, the problem set will be totally different, but this is something that you can do. So let's take a look at how we go from modeling data. So we've talked a lot about how we model data to how we actually query or search for data in the actualized version of that model. So we've modeled our data. So for example, we've modeled our data. We have taken that model, and we'll talk a little bit how we actually do that in the next slide. We've taken that model and we've put that model into the database and we've populated it with data. So with a bit of practice, entity relationship models can be used to actually plan these queries. And because we have that representation, we can think about how we're going to get data that's in there. So you look at the diagram and you figure out how to get useful information. And so, for example, if you can't find that information that you need, then you may need to look at how you have it designed. So think about how, for the purposes of your project, and if you do this, if you're starting a company or going into this industry, think about how you're going to query the data, the types of queries that you're going to ask for, the types of things or questions you're going to raise to the database. And if you can raise those questions, then you've got a pretty good, you're probably 80 to 90% of the way there with respect to design. So for example, using this model here, how can you find a list of students who are enrolled in an information systems class, right? Can you do that? And I'm not going to answer it for you, but I want you to think about it. Can you do that using this model, or potentially the model that we had on the last page? So let's move on to the next slide, slide 21 of 28. A bit about and talk about the languages of databases. How you actually can define that model, take that model and put it into a language so that it can be defined in a database, how you can manipulate data in that database, and how you can query for data in that database. So the most common term that you hear when you talk about database languages is SQL, and I dare to say probably a good number of you have heard of this. Structured query language, so structured query language, in a very strict sense, is used only for querying or retrieving data from a relational database. For example, this is an actual SQL statement, select first name from students, a very simple example that retrieves a list of first names from a student table. And so the reason why I said in a strict sense is because a lot of times people will refer to the activities or things that you do with respect to data manipulation language and data definition language as SQL. So, but to educate people on this, it's good to divide them up into three because they have three very different language sets. So the next one we'll talk about is data manipulation language, which is used for inserting, deleting, or updating data in a relational database. An example of that is update students, set first name equal to Matt or last name equals Levy. An actual DML statement. Updates all records with the last name Levy to have the first name Matt. That's what it does. Then the third one is actually how we define the structure of databases, data definition language, where one example of this is create table students with an ID field that's an integer, that's the primary key, the first name, which is a text field, that can be null. That's what null means. Null means it can be empty, so we can not have a first name for some reason. And then last name, which has a text field of 50 characters that can also be null. And so that creates a student's table with the fields first name, last name, and ID field as the primary key. So let's move to the next slide and talk a little bit more about the languages of databases. In contrast to non-relational databases, in contrast, non-relational databases use a variety of full-fledged programming languages, as opposed to just SQL. Across all the different types of relational databases, they all use SQL to query. But with non-relational databases, full-fledged programming languages are used, with what's known as application programming interfaces that are built by the vendor of that database, so that the people who know Java or C++ or C# or JavaScript can use that API to access data in the database. And so that's one of the very key differences, and we'll talk some more about these key differences in the next few slides. So I think this notion of non-relational database stuff is really cool, especially because of some of the advantages it gives you. Now, there's certainly lots of reasons to use relational databases, but let's talk a little bit about non-relational databases, which we also refer to as unstructured databases or NoSQL databases, as opposed to SQL databases. So these NoSQL databases encompass a wide variety of different database technologies, and they were developed in response to a rise in the volume of data stored about users, objects, products, the frequency in which this data is accessed, usually very rapidly, and the performance and processing needs that people really need with high transaction environments. So relational databases were not coped to scale with the scale and agility challenges that face modern applications, nor were they built to take advantage of cheap storage and processing power available today. So essentially, what I mean by that is that relational databases were built. The entity relationship model was built to make databases easier to search because it was very difficult and very expensive to have the necessary computing power to search unstructured data. That's changed, especially with some of the things we'll talk about later in the semester with regard to the compute power available in the cloud. So now that compute power is readily available. And so in some cases, you may not need to structure your databases. So let's talk about NoSQL database types. So there's 4 major types of NoSQL databases. There's document stores, graph stores, key value stores, and wide column stores. So document databases are, they're pretty simple, and most of these are actually very simple, with the exception of wide column stores, which may be a little bit difficult to conceptualize. But document databases are, they're document-based. They pair a key, a unique identifier, with a complex data structure known as a document, and that document can be something very simple, like a few lines of text, or it could be something very complex, like an encrypted Word document, or encrypted PDF, or a big giant blob of data. And so documents, they can contain many key value pairs themselves, have arrays of key value pairs, or nested, or even have nested documents. So they can be multidimensional in that sense. There's also graph stores, which are a little bit hard to conceptualize as well, which are mainly there to mine information about relationships. So by definition, graph stores are used to store information about networks, and social connections are a good example of that. Graph stores are used a lot in things like targeted marketing, where it can find relationships between disparate sets of data, and that information can be made actionable very quickly. The simplest of NoSQL databases is key value stores, where every single item in the database is stored as an attribute or key together with its value. And then the last one is wide column stores, which are generally optimized for huge queries, big queries over large data sets, and store columns of data together instead of rows. Google, for example, has a database called Bigtable, and they've recently made Bigtable available for people who use Google App Engine and want to use Google as a platform to mine large data sets. They can use their Bigtable algorithms to search over those things. So let's talk a little bit more about the benefits of NoSQL in this next slide. So first of all, it's more scalable. You don't have to worry about a relational model. You just have blobs of data, and it's much easier to scale that than something that has a complex model, and you're worried as to whether or not and where that data is and how to duplicate it. That becomes very complex with regard to relational databases. So for that, it can really provide some very superior performance. A data model, for example, addresses several issues that a relational model is not designed to address. So stuff in NoSQL addresses several issues that a relational model is not designed to address. And it's particularly with respect to large volumes of structured, semi-structured, and unstructured data. It also supports quick iterations, like agile sprints, and we'll talk about what that means later in the semester. But basically, to help you understand that benefit, is that you don't necessarily have to constantly worry about iterating your model forward. You can just start adding data to the database, to these NoSQL databases, and search on them, and rapidly get the information you need. Because that's what it's all about, is you want to be able to get that information you need as quickly as possible, and as cost-effective as possible to the organization. So object-oriented programming is also something that's a benefit. Because like I showed you with those languages, a lot of them are object-oriented. Java's object-oriented, C#, C++, JavaScript is kind of prototype-oriented, which is something like object-oriented programming. And then also another benefit is that it's efficient. It's because it's just these blobs of unstructured data, scaling out is a lot less expensive because you don't have this notion of a relational model that's rather monolithic in its intent. Another benefit is that you have dynamic schemas where you have no predefined relational model, which we kind of talked about in the last 2 bullet points there. Because you don't have a predefined relational model, it's very easy to scale. You've also got auto sharding, which because you have these blobs of data, it makes it very easy to store data across multiple machines. For example, Google servers, replicate data. Your data, our data, is replicated, all over the world. It's, strategically stored in areas so that we can get to it quickly, but it's replicated all over. And then one of the last benefits, and these are just a few, there's many more, is the notion of integrated caching. And this is just something that's part of the products, these NoSQL products that you can have, that you can download or buy. And a lot of them are open source, they're free. For example, Mongo is free for all. So integrated caching, which basically means storing data in a place in memory where it can be quickly retrieved to serve requests. Now with these benefits come a few considerations, right? Selecting the appropriate data model, you have to know what kind of, the general notion of the data that you're going to need, or you're going to have, whether or not you want to go with a document, wide column, graph, or key value store. And then there's, of course, the pros and cons of having consistent and eventually consistent systems, which basically means having multiple copies of data across different servers or services for high availability. Some of the common relational databases you'll see in the market are ones we have listed below, and I've classified it into those 4 categories. The ones you'll see, DynamoDB, it says it's in beta, I don't think it's in beta anymore. BerkeleyDB, Redis, these are key value stores. I've used Redis, and all it is a very, very simple database where you just, enumerate a key or give it or put in a value, it gives you a key, you can search on that key, and stuff is just really flat and really quick to access. And that's what it's for. Caching, Redis is great for intelligent caching, and that's what I've used it for in the past. Graph databases, I haven't used these. Neo4j, Infinite Graph, Sones, there's a few other out there as well. Column databases, HBase, React, Cassandra. Cassandra's, I think, one of the more popular ones. And then not on here is Google's Bigtable. And then the last are these document stores, CouchDB, MongoDB, and TerraStore. I've used MongoDB, and it's a full JavaScript implementation, and I found it extremely easy to use compared to most relational databases. Fantastic product, very quick access to data, and lots of services out there that will actually host things like Mongo and a lot of these databases for you, so you don't have to worry about setting up that infrastructure. So I think it's really cool that they've got these things available. And what's also interesting is that a lot of these are open source, free, are very, very cheap to use. So that's pretty much all I have with respect to our understanding of structured and unstructured databases. We're going to enact a lot of what we talked about here in our projects, and so I figured that it would be a really good idea to spend time just talking about how we model data, and hopefully you guys can use these slides and go back through them during your projects and use them so that it'll be a little bit easier for you to model your data. Because we're just going to work with relational models. Well, let me rephrase that. If you want to work with a NoSQL database, you can explain to me the business problem, and we talk about how you can actually actualize that. So hopefully this serves as a good cheat sheet for you, for your exams, of course, and for your project, and it's usable for you. And I will see you next time.